We're going to cover the idea of elevation, relief, terrain, and then how those concepts or those values are used in mapping and in GIS. When we're talking about terrain, we're talking about that three-dimensional aspect of the landscape or of the surface. It's the undulating up and down topography. So when we're getting information about elevation, that would be the z value of a coordinate. For example, this is a cross-section from Google Earth from the top of 30th Street Hill in Eugene near the college, and you see the profile down to where the college sits, and then on the west side going up. And the top of the hill is at about 867 feet above sea level. The college, I think, is around 400 and some feet above sea level. So the relief is the difference in elevation between the top of the hill and whatever location I want to study or describe. In this case, it would be the college. So the difference between 465 feet in elevation and 400 and whatever the college is feet in elevation, that would be the relief. You often see that indicated along with the geographic coordinates, where you have the latitude, the longitude, and then the z value. So relief will change depending on the scale that you're talking about. If I'm looking at the relief in Eugene, I might be looking at the difference between the highest butte and Coburg Road, which might be a lower section of the immediate area. If I'm looking at the relief across the whole state, I might be looking at the difference between sea level and the top of Mount Hood, whatever that value is. The concept of elevation and terrain and relief are really important. One, they help you just establish your location. You describe where you are based on high elevation and low elevation, places that can be seen and easily recognized, so landmarks on the landscape. So, you know, if you're standing and looking at the butte, you're looking south, and then that helps establish where you are. If you're using a topographic map, you often try to find those high features on the topographic map as places that you can help triangulate your location or know where you are. However, it has a much more or another use when looking at the analysis or the really fun part of GIS and geography. You need to know the relief and the elevation when you want to calculate the stream flow. You need to know the aspect. You need to know the slope. When you want to plan for urban stormwater runoff, you need to know the relief. Which direction is it going to flow? How fast is it going to flow based on how big the slope is? When you're trying to site a solar panel or a wind turbine, that understanding where is your wind current going to be impacted by a high elevation feature, or what aspect of the hill face is going to get the most wind. Resources. Timber cutting on a steep slope is going to be different. Replanting on a steep slope is going to be different. Looking at landslide potential. Relief and elevation and slope are critical for that. So these are just a few ideas in resource planning that you would really need to use the idea of relief. We can divide relief into two relative categories, or the expression of relief on maps into two different categories. One would be relative relief, and the other would be absolute relief. And these kind of correlate with relative location and absolute location. So relative relief gives you a general impression of the area. You don't really know exactly how high one place is on a map that's just showing relative relief. You don't really know how low another place is, but you know that one section is higher than the other section. And that can be done with color, that can be done with symbols, it could be done using actual raised relief on a map. The absolute relief gives you a number. It is telling you this spot is 50 feet. This spot is 100 feet. The relief between these two places is 100 minus 50, or 50 feet. So that number, that absolute relief, can be seen on topographic maps and is needed for analysis. I can't do a terrain analysis or a slope analysis giving generalities. So our absolute relief that we use is based on the mean sea level. So the mean sea level is 0 elevation. And then spot elevations and U.S. benchmarks are based on distance in elevation or altitude above that beginning value of the mean sea level. Spot elevations are will show up on a topographic map with an X. The USGS benchmarks are much more accurate. They're precisely surveyed in. They will often have a circular brass cap, or I've seen a silver metal cap. I don't think it's silver. I don't know if it's nickel. I don't know what they use for that. But the brass caps are very common. Often it will give you the datum. It'll give you, so this one is 717 feet above sea level, and give you the date when that was surveyed in. On a topographic map, a spot elevation will just have an X with the number beside it. Now, in order to understand what the units are for that map, you'll need to look at the bottom of the map to see whether they're creating the units are in feet or meters. Most U.S. topographic maps, I think elevation is in feet. The benchmark usually has an X with the letters BM. So if you were able to find this benchmark, you would more than likely be able to, or you should be able to find the brass cap that gives that elevation. So that's 241 feet. That is 220 feet. So if you didn't know, if you had a section of a map that didn't tell you whether this was feet or meters, there's lots of resources you have now that you could find that. You could go to ArcGIS Online and load their topo base map. And if you come up in this area with something at 200 and you know it's feet on that map, then you can pretty much estimate or be reassured that you have the right units. You can also see spot elevations at the top of a mountain or a hillside, which you may see a triangle with an elevation mark by that triangle. Elevation in water are using acoustic pulses, so they're called soundings. These are not based on mean sea level. They are based on the 19-year average of low water. And the reason they want to use low water, or the low water sounding, is because the bottom of the sea is critical to navigation. So they don't want to make a mistake on the highest or the average sea level. They want to know what is the depth to the bottom of the surface or the bottom of the ocean when the water is at its lowest. And then if you're sailing at high tide, you know you have that much extra wiggle room before you touch bottom. If you're sailing or navigating at low tide, that's the value you need to know. The term isoline is used in many different disciplines, and it means just a line of continuous value. So on topographic maps, the line of continuous value is a contour line. If you were looking at a weather map, it would be an air pressure line, an isobar. Temperature would be an isotherm. These lines of elevation soundings are isobaths. So supposedly, if I were able to walk along the bottom of the ocean at 50 fathoms, I should be able to walk right along this line and stay at a constant or nearly constant 50 fathoms. Isobars, looking at the barometric pressure. So what that is saying is that right along this area, the barometric pressure is 1024, and as long as I'm staying along that line, the barometric pressure is not going to change. Now, contour lines are based on elevation, and historically, surveyors would go out and set up surveying equipment and take the elevation at different points along the landscape, and then when you label those points of elevation, you can begin to sort of extrapolate between points and play a little bit of connect the dots. So here is a 40 foot of elevation, and here's 35, and there's 0. So if I were to say, okay, I'm going to start with that 30 foot of elevation, and 30 feet generally runs right around here. So there's 30 feet of elevation. And then I'm going to now make a line, a contour line at 40 feet of elevation. And I would just continue to connect the dots there. And I would fill in the entire landscape, having some of the dots between the contour lines as I extrapolate from one place to the next. And so if this were a small island, 0 would be sea level. And then I have a 10-foot contour, so I've gone up in elevation 10 feet. Then here is a 20-foot contour. I've climbed another 20 feet in elevation, 30 feet in elevation. Now there's a little distance between the 30 and the 40-foot contour. And then here, supposedly, I'm right at the top of the island. This distance between the contour lines is called the contour interval. And on this little sketch, the contour interval is 10 feet. If we were to look at a contour map in kind of a side view or a cutaway view, you can see that from a bird's eye view, this island has contour lines from sea level at 0, and the contour interval on this image is 500 feet. So this next line would be 500 feet in elevation, 1,000, 15, 2,000, 2,500, and then the top of this little hill would be 3,000 feet in elevation. There might be a spot elevation triangle or an X at the top of the hill that gives me the exact elevation, but if it doesn't, the most I can say is 3,000 feet. I don't really know if that mounds up or if it's flat. So my elevation point for the top of this, unless I have a spot elevation, would have to be 3,000 feet. If we look at it in side view, you can see that this west side of the island has a much more gentle slope than the east side of the island. But you can also see that on the contour lines in the overhead view. So here the contour lines are far apart. Here in the northeast section here, the contour lines are much closer together. And so over this distance, there's there's fewer contour lines, and the contour lines are farther apart. Here, the contour lines are very close together over a very short distance, which indicates a much steeper slope. And you can also draw that island or a similar island in a elevation profile. And Google Earth does this really well and much easier. Let me pull that up. So I have Google Earth open, and I zoomed into Mount Hood. I'm going to see if I can, I want to make that smaller so you can see the whole screen when I do this. So right now I'm going to use the path tool, and I want to show the elevation profile. And I'm going to go from this northwest section of Mount Hood over the top. I picked like pretty steep on both sides of the mountain. So that example didn't work very well because I couldn't find a topo of Mount Hood quick enough. So on Google Maps, actually, you can switch to terrain view, which will give you, just pull this in there, a really nice image of topographic. You can see the contour lines plus the shading. Anyway, so this is that, you can kind of see a gentle slope, and then right here it gets a little steeper. These contour lines are a lot closer together.